Hello! In our last video, we introduced logarithms and exponentials and we learned some important rules that pertain to both types of expressions. In this video, we're going to go a little bit deeper and we're going to talk about logarithmic functions and exponential functions, the way they look on a graph, and then things like domain and range. Before we go into this new material though, we need to introduce Euler's number. Euler's number is a constant, denoted by the letter E, and this constant is equal to 2.71828 ... It goes on forever. It is a never-ending decimal number. It's irrational, a lot like pi. Now, you've experienced pi enough that whenever you see pi in a math problem, you know that that's equal to 3.14159, whatever it is. And it just keeps going on forever. So when you see pi, you know that's just a number, 3.14. E is very much like that. E is just a number, 2.7. So whenever you see E in an expression or in a function, don't panic. It's just a number. It would be the same as saying, 2.7 to the x power or something like that. It's just a number. Now, there's a button on your calculator. If you have like a TI-84 Plus, there's a little button, just the letter lowercase e. And if you punch that into a calculator, it will be equal to this number right here. So you've got a calculator button for it. You don't have to memorize this number or punch it in every time. Just use the shortcut. The reason E is so important is that this constant occurs naturally in a variety of real-world contexts. You see it a lot in accounting and population growth. It's a number that occurs in the real world. It's just a pattern that mathematicians and scientists were able to pick up on, kind of like pi. Pi is just a natural number that occurs in patterns all over in real-world contexts. Very frequently, you'll see e to a power. That's where this number e finds itself being used most often. The patterns that people have noticed are exponential patterns related to this base e. So since e occurs in the context of exponentials and logarithms quite frequently, e to the x is one expression you'll see a lot, but also since exponentials and logarithms are inverses of each other, we also encounter log base e all the time, just its inverse. But log base e, I guess, was taking us too long to write, so we decided to give log base e a special name. We call it the natural log, and it's denoted as ln. I think that's probably Latin. It's the reason the letters are switched. There's another Latin name for it where the words are reversed. So ln is the natural log, which is just log-based e. So you might frequently see things like ln x. Well, this is just the inverse of e to the x. So these two things are inverses of each other. So let's go, now that we know or understand what e represents, let's talk about exponential functions and some of the rules we're going to need to know pertaining to exponential functions. So first of all, when we introduce a new function, we're going to want to talk about its domain and range. Exponential functions are things like 2 to the x or 7.9 to the x or even e to the x. These are all exponential functions. Exponential functions have an unrestricted domain. There is nothing preventing us from putting any number we want to in here for x. So our domain is going to be all real numbers. For all exponential functions, that's your domain. We never have to worry about it. Our range, however, is not all real numbers. Our range is going to be restricted, and let's talk about why. Anything to the power of x can never equal 0. Think about it. Take this first example, 2 to the x power. We could never make this equal 0, no matter what we put in for x. So if we put, let's say, a really big number in for x, you'd get 2 to the power of some huge number. That would give you some really massive y value. If we put 0 in for x, that would give us 2 to the 0 power, which is 1. Anything to the 0 power is always equal to 1. And finally, even if we put a negative number in for x, if we put a negative number in for x, so like 2 to the negative 5, let's do that. 2 to the negative 5 is the same as 1 over 2 to the 5th. So yeah, this is going to be some kind of small fraction, but it's still a positive number. Our range values, our y values, will always be positive numbers. And as we let that exponent become even more and more negative, we'll get even smaller fractions. I'm not even going to try to guess what 2 to the 100 power is, but this will be some sort of insanely small fraction. But it still won't be 0. It will never actually get to 0. There is no way to turn an exponential into a 0. It's impossible. So when we're talking about range, our y values will always be bigger than 0. I suppose I should have said this, but you can never make it negative either. It can't be 0 and it can't become negative. It will either become a really, really small fraction, but a positive fraction, or maybe a really, really big number. And so that would be represented by the y values some lowest value up to positive infinity. Now, our lowest value might be different in different problems, but if we're using 2 to the x as an example, we can get our 2 to the x to be as small as we want, but it will never actually be 0. So as long as we keep making this number grow, our fraction becomes smaller and smaller and smaller, so it's approaching 0, but it will never actually arrive at 0. So I do want to reiterate that this number will not be the same every time. We will be restricting our range. So we have a word for a value that our function is getting closer and closer and closer and closer to, but it'll never actually reach it. That is called a horizontal asymptote. Well, it's horizontal asymptote because it's a y value. So just to recall, an asymptote is a line that the function will never intersect. It'll never actually cross it. It'll never actually reach it. So our asymptote is what's going to determine our range. So let's do a few quick examples to see if we might notice a pattern. So first we're going to find the domain and range of f of x equals 2 to the x. Well, we already kind of did this. Our domain is always going to be all real numbers for an exponential. And here, as we make x a smaller and smaller and smaller number, meaning a more and more negative number, as we keep making this more negative, the fraction that it produces is going to keep becoming a smaller and smaller fraction. So ultimately, we are going to end up approaching the number 0, but never actually achieving it. And then our range goes all the way up to positive infinity. For the second example, we want to find the domain and range of e to the x minus 1. Our domain is negative infinity to positive infinity. We don't have to restrict the domain. We're allowed to put any number we want to in for x. Now let's talk about what happens to the y values when we do that. Just like with 2 to the x, e to the x has a positive base. E, remember, is just like 2.71. Yeah, 2.71. So this is just like 2.71 to the x power minus 1. And as we make x bigger, this value will get bigger. So that's going all the way up to positive infinity. But as we make x smaller, smaller and smaller and smaller, meaning it's becoming more and more and more negative, then we end up with this fraction to some number. As we make our negative number bigger and bigger and bigger, say all the way up to negative 100, this becomes smaller and smaller and smaller. So it's approaching 0, but it never actually quite reaches 0. But then this is approaching 0, but then we subtract 1 from that. So we would have 0, what we're approaching, minus 1, would mean that our range might make it all the way down really, really close to negative 1, but not quite actually ever achieving negative 1. And that's what this parenthesis indicates. All right, one more example. For the last one, we want to find the domain and range of f of x is equal to negative 3 times 4 to the x plus 2. So in this example, as we let x get closer and closer and closer to really, really low negative values, this 4 to the x is getting closer and closer and closer to 0, which means the negative 3 times x is getting, or times 4 to the x is getting closer and closer and closer to 0. So this whole first term is getting close to 0, really, really close to 0. And then we're going to add 2 to it. So our range would include, or it would go all the way up to positive 2. Now, we have to consider, are we looking at a 2 to infinity, or are we looking at a negative infinity to 2? And the reason I asked that question is because this example starts with a negative. We're going to address this in just a moment, but you have to think back to parent functions. A parent function, like 4 to the x, would have a range from 0 to infinity. But then if we were to stick a negative out front, it would flip it upside down. It would reflect it over the x-axis, which would put all of our values below the axis, meaning that they would all be negative. So just thinking about these conceptually, we would end up with all of the negative values going all the way up to positive 2. So it's actually, our range here is actually negative infinity to positive 2. And we just had a kind of conceptual conversation. There are other ways to find the range, and we'll talk about those in a little while. One really effective way of finding your domain and range is to actually just look at these on a graph. Pull out your graphing calculator, punch this in, and then look at a graph on like a TI-84 Plus. You'll be able to visually see your domain and range. You'll be able to visually see how this negative flips your exponential upside down, for instance. So for the purposes of this conceptual conversation, it might be a good idea just to look at these on a graph. All right, that brings us to parent functions. We kind of segued into this already. Exponential parent functions all look like variations of what you're seeing on this graph. Here are 3 different parent functions. We have a 2 to the x parent function. It's a curve. Notice it passes through the point 0, 1, because if you had 2 to the 0 power, that would be equal to 1, so you get the point 0, 1. The next parent function that's listed here is y equals e to the x. Now remember, e is just, it's approximately equal to 2.71, so it's going to be pretty similar to 2 to the x. You know, 2 to the x and 2.7 to the x are going to be kind of similar to each other. Notice this one also crosses through the point 0, 1. That's our y-intercept. Because if you took 2.71 to the 0 power, that would be 1. Anything to the 0 power is equal to 1. So our y-intercept on these is always going to be 1. All right, finally we have the parent function y equals 3 to the x. And if we took that to the 0 power, that's also equal to 1. So 0, 1 is the y-intercept of this one as well. So our parent exponential functions are all going to pass through 0, 1, and they're going to be sort of an upward slanting curve. And notice as our base gets bigger, our curve gets steeper. So if I wanted to find, y equals 4 to the x, it's probably something like this, right? It'll be even further to the left than 3 to the x power. So one other thing to notice is that we're going to have a different parent function for each base, right? 2 to the x is a different parent function than e to the x, which is a different parent function than 3 to the x. So these all 3 would be considered parent functions. It's not like you just have one exponential parent function. You've got one for each base. We're going to use what we just talked about to answer some example problems. These questions come from the common version of homework 11A. So feel free to go to the common version of homework 11A and kind of work alongside me if you want some extra practice. So this question, question 10, asks us to consider the function f of x equals negative 8 to the x. If we express the range of f of x in the form of a comma b, so interval notation, and we use c for the equation of the asymptote, ooh, that brings me to something that I kind of glazed over. If we go back to our domain and range examples we did a few minutes ago, basically what each of these is telling us, so for the first one, our function is getting really, really, really close to 0, but it's never actually going to touch 0. So we're going to have a horizontal asymptote at 0. So an asymptote at y equals 0. For the next example, our function is going to get really, really, really close to -1, but it's never going to actually cross it. So we have a horizontal asymptote at y equals -1, and that informs our range as well. And then finally, for our last example, we had an upside down exponential that's approaching 2. So we'll have a horizontal asymptote at +2, and that informs our range as well. So take a look at these numbers. I'm going to circle them for us. Our asymptote is at y equals 0, which means our range starts at 0. This asymptote is at y equals -1, which means our range starts at -1. And this asymptote is y equals 2, because our range ends at 2. In the original questions, look at this number that's added at the end. +2 showed up here. -1 showed up here. And in our first example, there was nothing there. There was no number added at the end, so we could just imagine there's a +0 shows up here. So if you have an exponential written in the form f of x equals ab to the x plus c, c is going to be your horizontal asymptote. Which also in turn informs your range. So your range would either be -infinity to c or from c to +infinity, depending on whether you're dealing with a positive exponential function or a negative exponential function. So if a is positive, you'll get this model. Oh, nope, I did that backwards. If a is negative, you'll get this model, and if a is positive, you'll get this model. So just a few patterns to show you. You can figure all of this out kind of the long way, but I like shortcuts. I think they'll save you some time. So let's use some of those shortcuts and dive right back into question 10. So our function, f of x, is equal to -8 to the x power. So first we want to find the asymptote and the range. Well, the asymptote and the range are closely tied together. The asymptote would be whatever number is added at the end of our function, but there is no constant added there. So our asymptote is going to be at y equals 0. And when they ask us to put our answer in, they call it c, because they say y equals c. We're going to put 0 in as our c. Then that informs our range. So our range is either going to be -infinity to 0 or 0 to infinity, and we have to figure out which one. Well, that's based on whether there's a negative sign in front of your exponential. Since we do have a negative here, that's going to flip our exponential upside down on the graph. So it'll be somewhere in this ballpark, which makes our range go from -infinity to 0. So I'm going to erase the rest of these notes. And I'm just trying to show you here the logic that I would use to find the range of a function without having to do a lot of complicated algebra. So they're asking us to express in the form of interval notation. So from a to b, that makes a -infinity and b 0. Moving on to question 14. We have a function this time. It's another exponential function, and it's written sort of out of order. Typically, I like to write these with my exponential first, so I'll have 1/4 to the x power minus 2. Makes it a little easier to see. This number that's added at the end is our horizontal asymptote. So y equals -2 is our asymptote, which helps inform our range. So our range, let's see, where's -2? Our asymptote would be here at -2. So our function's either going to have a range that's above the asymptote or below the asymptote. And which one it is depends on whether this out front is positive or negative. And since there's no negative number out there, this is a positive. So our function's going to be above our asymptote, approaching the asymptote. So that would give us the range of -2 to infinity. Both sides have parentheses, so we fill that in here. And we already discussed our asymptote, which is where c equals -2 comes from. In example 28 from the common version of the homework, this time we have an e to the x plus 2. So f of x equals e to the x plus 2 and then -4. In this problem, our base is e, which is basically about 2.71. That's just a number, don't let that throw you off. And also, the fact that we have this other plus 2 up here in our exponent doesn't really affect anything, because we're going to be looking for what happens when we make our x values super, super negative. So we might end up with something like e to the -100 plus 2, which would just be e to the -98. So we can make this number as negative as we want, despite the fact that this plus 2 is here. We'll just keep making it even smaller. If I wanted, I could say, well, let's take e to the -102 instead, and I'd get -102 plus 2, which is e to the -100. So we can make that exponent as negative as we want. And as we've discussed a few times already, as we make that exponent more and more and more negative, this piece of our exponential function approaches 0. It will never actually reach 0, but it will get really, really, really close to 0. And then we'll be subtracting 4 from that. So our y asymptote is y equals -4. So let's draw this on a graph really quickly. Y equals -4, let's say it's right here. Now let's figure out if our function approaches this asymptote from above it or below it. Well, this is a positive. There's no negative out front. So that means we're going to be above, approaching from this side. So something like this. So that helps us identify our range. It will go all the way down to -4, but it won't include -4, and then all the way up to positive infinity. So that's where we get our A, our B, and our C from the start of the range, the end of the range, and the asymptote value. Okay, let's do a problem involving graphical representations of exponentials. So keep your parent functions in mind. If all of our exponential parent functions go through the point 0, 1, and if this is 2 to the x, then 3 to the x kind of looks like this, and 6 to the x would look more like this, right? So each one gets a little bit skinnier, and it'll have a sharper curve. So our 6 to the x parent function would look something like this. So first we're asked to find 6 to the x. Then we're going to be flipping things around. So we'll do a -6 to the x plus 4, things like that. And we'll have to figure out, using transformations, how that's going to shift our graph around on the coordinate plane. So the parent function is d right here. So take our picture and compare it to the 4 pictures available. This d is our parent function. So that would be this first one. So that's why we've selected D as our answer here. So D is already taken. Let's look at the other ones. All right, so if we have, the second one is -6 to the x plus 4. The effect that the negative has is to flip this across the x-axis. So it flips it upside down. So if I were to redraw that on my graph, it would look like this. It would just be the upside down version. Then we have a plus 4 on the outside of the function, just kind of at the end. You know, you can cut these off completely from each other. We're just throwing a plus 4 at the end of the function. That's going to be a shift up 4 units. So take the red graph that I drew and shift it up 1, 2, 3, 4. Our function would end up about here. So we're looking for this on a graph, on one of our graphs. It looks like C. C would be the answer to this one. So this is just transformations. We've already used C and D. Let's try to find the other two. So our next function is f of x equals 6 to the x minus 4. So we're subtracting 4 in this problem, but we're subtracting it within the function. This is within the exponential, not on the outside like in the last one. So this minus 4 doesn't move it up or down. This minus 4 moves it left or right. And if it's inside the function, it does the opposite of what you think it would do. So this minus 4 is actually a right 4. So I'm going to erase my previous mark here. And we're going to draw our new one. So start with your parent function, shift it right 1, 2, 3, 4 units, and it should look something like this. It's just shifting it right 4 units. So it looks like our option here is A. We get A as our answer for this one. And by process of elimination, we can probably figure out what the last one's going to be, but I want to do it anyway. 6 to the negative x. What we've done is we've put a negative in front of the x value. So this flips our function, but it flips it over the y-axis. A y-axis flip is a left-right flip. So what that's going to do is it's going to take my function and reflect it across the y-axis. So that's B. I hope you remember your parent functions and your transformations. These things will keep popping up in this class. Now it's time to move on to logarithmic functions. So we've just discussed what exponentials look like on a graph. Now let's talk about what their inverse, logarithms, look like on a graph. With logarithms, our range is going to be all real numbers, but our domain is restricted. And that was the opposite for exponentials, right? For exponentials, our domain was all real numbers and our range was restricted. Well, that's what happens when you're dealing with inverses. They'll kind of be the reverse of each other when it comes to domain and range. So I have a note here for you. You can never take a logarithm of the number 0 or of negative numbers. And let me show you why. So we'll do 2 examples. Let's do log base 2 of 0 equals x. If I tried to take this logarithm, log base 2 of 0, let's rewrite this as an exponential. So we would have 2 to the x power equals 0. We discussed above that this is impossible. We can make 2 to the x power really, really, really small. As we make x more and more negative, this becomes a smaller and smaller and smaller fraction, but it will never be able to equal 0. Exponentials can never equal 0. So we're just going to draw a big X through this. This can't happen. What that tells us is I'm not allowed to plug 0 in here. It's undefined. If you try to plug 0 into a log, your calculator will say, error, can't do it. It's like trying to divide by 0. You can't take the log of 0. Let's do one more example with a negative number. If I had log base 2 of negative 1 equals x, and I converted that into an exponential, we would get 2 to the x power equals negative 1. This is also impossible because no matter what value we put in for x, 2 to the x power will always be a positive number because the base itself is a positive number. So it will be impossible to achieve a 0 or a negative, which means it is undefined to try to take the log of a 0 or of a negative. So here's what we do. To find the domain of a logarithmic function, we set the log's operand greater than or equal to 0. So if I had, let's just do the example below. If I wanted to find the domain and range of f of x equals natural log of x minus 4 plus 17, the range is easy. We'll do that first. The range of a logarithm is always negative infinity to positive infinity. The domain, on the other hand, I'm not allowed to take the natural log of negatives or of 0. So x minus 4, has to be greater than 0. It's not greater than or equal to, because remember, it's not allowed to be equal to 0. It has to be greater than 0. So then we find the set of x values that make that possible, and we would restrict our domain. Our domain would have to be x is greater than 4, so that would be from 4 to infinity. If we look at our logarithmic parent functions, we can even kind of see this pattern on a graph. These are parent functions, so they are our most basic version. We start off up here with log base 2 of x, and then we've got log base e of x. Remember, e is 2.71. So we have log base 2, log base 2.71, and then it keeps going down each time, and then they show us log base 10, which is all the way down here. So each logarithm, each base, is going to have a different parent function, just like exponentials, and they're getting closer and closer and closer to the x-axis as we make that base bigger. Well, this pattern kind of looks familiar. Notice how each one of these goes through the point 1, 0. Do you remember what exponential functions went through? They went through the point 0, 1. So that is expected with inverses. We should see similar patterns reflected across a diagonal line. Kind of goes this way up through our graph. So just to reorient ourselves, remember that exponentials and logarithms are inverses. So a lot of the things that are true about exponentials are going to also be true about logarithms. For instance, exponential functions like this one have a horizontal asymptote. So their inverses, logarithmic functions, will have a vertical asymptote. Also, a couple of other things that you should note, some similarities between the two things. Already kind of pointed this out, but our exponential goes through the point 0, 1. Our logarithms go through the point 1, 0. And they should be mirror images of each other, reflected across this dotted line, this y equals x. So draw a perfect diagonal line with a slope of 1 that cuts your graph in half. These two inverse functions should be perfect reflections of each other. Now, this picture, notice, is for 2 to the x and log base 2. So these two things are inverses of each other. If instead we wanted to draw 3 to the x and log base 3, our pictures would look pretty similar but slightly different. So just use caution with things like that. Let's do some examples together. In this example, we want to, we start with the function g of x equals natural log of x plus 2 plus 3, and we want to find the domain. The domain of logs is restricted. It's restricted in this way. Whatever you're taking the log of has to be greater than 0. So then you solve for x, and that gives you your domain. So if x is greater than -2, that gives us the domain from bracket -2 to infinity. And that's where we get the -2 and infinity. Oh, I said bracket, I meant parenthesis. I'm having a long day. All right, so just like exponentials have a horizontal asymptote at that value, logarithms are going to have a vertical asymptote at that same value. So whatever value you used to restrict your domain will represent your vertical asymptote. So x equals -2 is a vertical asymptote. For the next example, we're going to do something very similar, but this problem is a little bit more complex. We have g of x equals log base 4 of x squared minus 64. So to solve this, or to find our domain, we have to restrict what's inside the log to be greater than 0. Now, I'm going to erase everything else. We don't even really care about our function anymore. Now what we're looking at is an inequality. To solve this, we're going to be using the test point method that we learned in Unit 10. So that was last chapter. You've already taken your quiz over this material, or you're at least working on your quiz over that material right now. But see, those skills are coming back, and we're reusing them in this new unit. So here's how we do this. First, we have to find our critical points. So we set x squared minus 64 equal to 0, and we solve for x. Well, that's going to give us x equals plus or minus 8. So we have two critical points, positive 8, negative 8. We draw a number line. We mark our critical points, and we choose test values within each interval. So the negative 8 and the positive 8 divide our number line into intervals, and we're going to choose a test point inside each one of these intervals. So I'll just use 0, because I love using 0, makes it easy, and -9 and +9. So first, let's plug in f of -9 to this expression, the one I just circled. -9 squared gives me positive 81, and positive 81 minus 64 is greater than 0. So this is greater than 0. That gives us a yes. We'll say greater than 0. Then when we plug 0 in, f of 0, we end up with 0 minus 64, which is -64, which is not greater than 0. So this part of our function would be down here below the graph somewhere. And then finally, when we plug in positive 9, you end up with 81 minus 64, which again is a positive number, so you're back up here. So we're restricting our domain to places where this expression is greater than 0. So that would be this part of our graph here. Let's do it in a different color. It would be this part of our graph here going all the way down to negative infinity, and this part of our graph here going all the way up to positive infinity. Notice that at -8, our function would be equal to 0. So that's not what we're looking for. We're looking for places where our function is greater than 0. So we're going to have this pattern for our domain, and that's negative infinity up to -8, parentheses, union 8 to positive infinity. So this is a bit of a recap of a skill we learned last week that's helping us now find domain in a logarithmic problem. All right, so you put in your A, your B, your C, and your D, and that's all this problem asks you to do. In number 25, we have two logarithms involved in this question. It says g of x equals natural log of x plus natural log of 2 minus x. No worries, all we have to do is restrict our domain. So our domain has to be restricted by ensuring that this is bigger than 0 and this has to be bigger than 0. So we're going to set up two different expressions. X has to be bigger than 0 and 2 minus x has to be bigger than 0. We'll solve both of these, so we get x is greater than 0. Over here we get negative x is greater than -2. When we divide both sides by a -1, that reverses our inequality. Anytime you multiply both sides by a negative or divide both sides by a negative, it flips your inequality symbol in the other direction. So we have two things on restricting x right now. So if I draw a number line, for x is greater than 0, if 0 is right here, x has to be greater than 0, which would be this area of our number line, and x has to be less than 2, which would be this area of our number line. Well, the only place where both of those things happen to be true is in between 0 and 2. So my interval is going to go from 0 to 2, close parentheses. All right. Vertical asymptotes are going to appear at x equals 0 and x equals 2. So we're going to put those values in here and here as our vertical asymptotes. Moving on to a question about using our parent function and transformations to identify graphs of various logarithmic functions. Remember, our parent function of a logarithm is going to go through the point 1, 0. It's going to have a vertical asymptote, so it's getting really, really close to 0, and then it's going to kind of just shoot up and off into the distance. That's our parent function. So now let's find these four various functions using transformations. So we're going to start at the top. It says negative natural log of, I'm going to reverse the order of this, negative x minus 3. I like to have my x in the front. And if I were to rewrite this, that would be negative natural log of negative parentheses x plus 3. Remember, an internal negative actually applies to both pieces, so you might have to essentially factor that out to see exactly what's living inside your function. So the first negative sign out front, that's a y-axis or an x-axis flip. It flips it upside down. The negative sign on the inside of the function is a y-axis flip. And then finally, the plus 3 inside these parentheses represents a shift left 3. Remember, it's the opposite of what you would expect. All right, so if we do these three shifts, we get an x-axis flip, which flips it upside down. Then we get a y-axis flip, which flips it over here. And then we get a shift left 3, that'll go from here to 1, 2, that'll go to here. So I'm going to erase the various stages. We are looking for something that matches this graph, and I see it right here, it's D. The next one we want to identify is negative natural log of negative x. This first negative out front represents an x-axis flip, and the negative on the inside represents a y-axis flip. And we actually had just drawn this, but I erased it. That would be our x-axis flip, and then our y-axis flip would put it like right here. So we're looking for a graph that shows this pattern, and I see it right here. So that's C. For the next one, we're dealing with negative natural log of x plus 3. The negative out front is a x-axis flip, and the plus 3 on the inside of the function represents a shift left 3. Remember, it's the opposite of what you would think it is. So I'm going to erase some of these marks. Let's do our shifting. So we start from our parent function, we flip it over the x-axis, and then we shift it left 1, 2, 3 units. So about here should be our answer, and that's A. And finally, one more transformation we have to do. We have negative 3 plus natural log of x. Well, we wouldn't write it that way. Let's write it as natural log of x minus 3. So the natural log of x is our parent function. We're not going to have to shift that at all. But the negative 3 out front tells us to shift down 3. So we take our parent function, we shift it down 3 units, and that gives us one that looks like this. So that would be B. There's our 4 answers. All right, that was the last example of the video. I hope that was helpful. I hope you also approach me in class if you have any questions about these videos or if you need any extra help with your homework. Good luck.